Enkeleida Lushi. I'm faculty at New Jersey Institute of Technology, and I want to thank Dave, Marco, and the UK Biofluids Network that invited me to give this seminar. It's always a pleasure. And I'll talk to you about microswimmer motion in confinement, or at least the work that I've been doing in the last few years in this direction. So, So a lot of this work is in the context of collective motion, and you've heard a lot about collective motion of motile agents, and of course you have experienced a lot of this. Collective motion is seen in a lot of biological agents, things from at the microscale, bacteria, algae, Spermatozoa, Paramecia. Lately there is a lot of work on active colloids on this, and you even see collective motion in birds, fishes, and human crowds. So each one of these units moves in its main kind of motion mode. For example, you have a self-propelled unit. It interacts with neighbors, right? And this interaction will depend on the type of agent, the medium, the shape, and so on. And then you get collective motion. So there is a lot of this work that is being touted as living active matter, right? So active matter, a lot of it is under this umbrella. And I specifically look at microswimmers, so things at the micron scale. So things like bacteria, algae, Spermatozoa, and colloids. So I will tell you a little bit about this work, right? So microswimmers. So the model microswimmers, as you've heard also in the other talks, are things like bacteria, microalgae, Spermatozoa, and lately there's work on active colloids. So I'll mention a little bit about work in all of these. So swimming bacteria, things like E. coli, Bacillus subtilis, right? E. coli, you've heard about it because usually that gives, it's about like there are pathogenic strains. And bacteria in general, most of them move by using flagella in their ear. So they have many flagella, and if they can bundle them, they propel themselves. But as they move, they do disturb the fluid flow. And if you visualize this fluid flow, it looks like this force dipole or hyperbolic fluid flow, right? Which the streamlines, you see they come in more or less in the middle of the swimmer, and that they come out at the front and back, right? So, and because this type of swimmer pushes itself forward using the flagella, it's called the so-called pusher swimmer, right? So it's a prototype pusher swimmer. Then we have chlamydomonas. It's a eukaryotic cell, kind of round, and it has two flagella in the front. And by moving these two flagella in a periodic motion, in a breaststroke kind of manner, it pulls itself. So it's a so-called puller swimmer. And the fluid flow that it generates, if you average it over one breaststroke cycle, is also this hyperbolic-like fluid flow, force dipole, but with a reverse sign from that of the bacteria. So the fluid flow, roughly, comes in at the front and back and goes out on the sides, right? Then there is Spermatozoa, and you've heard a lot of this from Dave and Murik. So they are also pusher swimmers because they push themselves with a flagellum in the back, but it's a single flagellum which undulates, right? But if you also time average over one undulation, you also get this hyperbolic-like fluid flow, right? So by and large, you can also describe it as the lowest order as a force dipole, right? The pusher swimmer. Right? So, and now there is a lot of work, as I mentioned, on these phoretic swimmers, right? So you can put together gold and platinum. A lot of this is rods or sometimes sphere. Now there's a lot of work on various other shapes as well. And if you put these particles in specific solutions, for example, hydrogen peroxide, then it moves. So it's technically a swimmer, and lots of these are in the micron scale. So a microswimmer, but very different motility. So in the end, I'll talk a little bit about these as well. So how do two pusher swimmer interact? The consensus has been that two pusher swimmers, like we see in the bacteria, they move together, they collide, and they co-swim. And that is due to the elongated shape and also to the fluid flows. These disturbance fluid flows that generate kind of push them together so they co-swim. And you see this in bacteria. Okay. And now you put a lot of these together and you get collective behavior. Right? So you put a lot of bacteria in a drop. So this would be Bacillus subtilis, it's this elongated bacterium, a few micron long. And you get this, we shouldn't call it turbulence, but so-called quasi-turbulence, which is this chaotic behavior over large length scales, larger than an individual, with enhanced speed, and you get to see correlated motions over longer scales than an individual. It's all self-organized, right? There is nothing telling the bacteria what to do or where to go. And there is a lot of other features, right? You get to see jets and vortices, transient jets and vortices. You get to see enhanced transport and diffusion. So this was kind of the work that sparked a lot of studies in the last 15 years, right? The work by John Kessler and Ray Goldstein and all. So I've been focused on looking at various models of microswimmers, right? So how do you build minimal enough microswimmers? And people have been dealing with models of various complexity, things like dumbbells, like two spheres connected by a rod or a spring, ellipsoids. The most prevalent one has been the squirmer model, which you have a sphere, right? So Tim Pedley has done a lot of work on this. You have a sphere where the tangential velocity on the surface of the sphere varies. And then you can look at individual collective behaviors. But what do you have to keep in mind about these microswimmers when you design models? First, they swim, right? They're in fluid. And if they swim, they also disturb the surrounding fluid. The other thing is if you have more than one, they do collide with neighbors eventually. And the majority of these swimmers are not spheres. Right? For bacteria, the vast majority, they are elongated or spirochetes. So we want to keep in mind all of these features when we design models, right? We want to design models that are minimal, but still capture the basics of the physics. So I like to put this picture of Picasso in here. Essentially, if you are Picasso and you want to draw a herd of thousands of bulls, you are not going to draw the details of every single one of them, right? Because that would take a long, long time. But you do want to include enough details, say like the horns, the legs, the tails, so that people know that's this particular animal. So that's kind of what we have to keep in mind when designing these models. We want to make them as minimal as possible while still maintaining enough correct physics. So one model that I've used extensively in the last few years is just that. So we model each swimmer as an ellipsoid, and we trace the center of mass and the main direction. So what these equations essentially say is each swimmer swims in its main axis of shape, right? With a constant speed, but one can vary it, right? It can be pushed around by, if there is any background fluid flow, it can be rotated by this fluid flow. That's the second equation. And we do include forces and torques in case this swimmer collides with neighbors, right? So that way they don't overlap. So forces and torques are there to avoid overlap and also these collisions. Then the other thing that this model includes is that it includes the fluid flow, right? So essentially all these contractile or extensile dipoles. So if you have a puller, you have a contractile dipole, and a pusher, this extensile force dipole. And by adding essentially the actions of all these dipoles, you get the collective fluid flow, right? So that's the Stokes equation. So this is kind of a short way of describing these equations, right? So it includes the actions of the fluids on the particles and also the effect, like this collective flow generated by each one of these swimmers. Then it comes to the implementation. I mean, many people have done various work in this. So we are coupling the dynamics of each swimmer, right? So it's a Lagrangian structure, and the fluid, which is typically solved in Eulerian grid, right? A lot of people use singularity methods, so I'll talk about the immersed boundary method. It's a way to go back and forth from a structure, like Lagrangian structure, to an Eulerian grid, an underlying grid, which is used to solve the fluid flow. I prefer this, it's pretty efficient, and you can solve the fluid flow in a periodic domain. right? And you can include shape-dependent collisions, right? So you can have spheres, ellipsoids, or anything more complicated if one desires. And one can solve this pretty in a fast manner, right? And the methodology is versatile. You can extend it to include domain boundaries, as I'll show later. The particles do not need to be uniform in speed or shape or type, right? You can have mixtures. And the other thing is the fluid doesn't need to be Newtonian or Stokes. So this is an advantage over singularity methods, which is predominantly Stokes flow. One disadvantage that this has is that it does not resolve near field fluid flows, right? Because what the immerse boundary method is, as I have in this figure in the top right corner, right? It essentially smoothes out these forces, right? So it's essentially smooths out the effect of the Stokeslet. So if you have a bacterium and you have these two Stokeslet, it smoothes out this, and as a result, you essentially have a smeared kind of Stokeslet effect, right? And for a bacterium, you have two Stokeslets that are smeared out. So there is no singularity per se. It's a smooth singularity, right? And the near field fluid flows are not resolved. So we want to see, does just including this, right, this force dipole, does this help, right? So it's a very minimal model, and coupling the fluid and the particles. So you put all of that together, and sure enough, you get collective behavior. The difference with this method is that it resolves not just the fluid flow, but also the collisions. And that can be like computationally extensive, but essentially you don't have particles that overlap, right? The ellipsoids don't go through each other, or, right? So it's more physically correct. But how do you know this collective behavior is right? Many people have looked at this method. Then another complication came into this, is that microswimmers in nature and in the lab, well, they're in some confinement. They're not in free space or periodic domains, obviously. So what you see in experiments, it's microalgae, for example, in a rectification device. That's the top left corner. Bacteria on a surface, you can get various structures, right? They stick to surfaces. Bacteria love surfaces. Spermatozoa in a rectification device. That's work from Dave and Peter Denisenko, etc. And if you put bacteria in a microchannel, even if there is imposed flow, like they can form biofilm because they like to stick to surfaces. Even our typical model microswimmers, right, biological swimmers like bacteria, algae, and Spermatozoa, they also don't live in simple enough kind of fluid flow. They live in some sort of porous structure. Bacteria live in soil or marine snow or, well, mammalian tissue. Algae, for example, are used in bioreactors, right? So you have these glass sponges and you have to, right? So it's a porous structure. And spermatozoa, as everyone knows, have to move through a network of filaments, right, to get where they have to go. So it's complex confinement, right? It's not simple. So we have to look at bacteria and these microswimmers in a more realistic manner. So the experiment that inspired a lot of this work in this direction was in the group of Ray Goldstein. This was quite a few years back. So Hugo, who did the experiment, essentially had a droplet of Bacillus subtilis covered in between two cover slips. So the droplet is kind of drum shaped. And so what happens? So what happens is that it self-organizes into this spiral vortex, which is stable for as long as there is oxygen for this bacteria. Right? So you can see a layer moving in one direction near the corner, and the middle moving in the opposite direction. Now, one thing that you'll notice is that it's difficult to visualize the flagella. So it's difficult to tell where the flagellum is with respect to the cell body. Right? So essentially the direction of motion of swimming is not obvious. So sure enough, one can modify this numerical method to include simple enough boundaries, like a water-oil drop interface. Right? It can be done. And what do you have? Well, here we have, and one can do this in 2D or 3D, but 2D is computationally easier. So what happens? You have a few swimmers, just because they're moving in some direction, they will hit the boundary. But because they're pushers, right, bacteria, they will stay there due to the shape and also due to the fluid flow that pushes them around the boundary, unless something else essentially knocks them outside. One thing you will notice is that a single swimmer here, it's moving at a very, very low angle against this boundary. So what happens if you have a few more swimmers? So these ones are a few more, so it's still a very dilute suspension. It's elongated swimmers. Eventually they do reach the boundary, but there they have to fight with the other swimmers. So you see, and then they have to swim together. And you will see that the ones at the boundary, because of the elongated shape, they are organizing and swimming at an angle, right? And this is not trivial angle, nothing you could think where they would go. So that's a function of the elongated shape and the self-propulsion. And they organize. And the ones that are left, they also try to go and find their place. What you will notice is that they're all moving in one direction, like all the swimmers, like the rotation is in one direction, but the fluid flow that emerges in the bulk is in the opposite direction. So they're pushing fluid flow back with their flagella, which act like micropumps, in the opposite direction, right? So the swimmers are moving in one direction and they're pushing fluid flow back. So, and also locally they're aligning, right? So because of the elongated shape, you get this aligning, local aligning. So what happens if you have a lot more of these? And this was not immediately trivial when we tried this work, because the consensus was that, well, it's very dense and the fluid flows are probably screened and should not matter. This was kind of the first experiment, a numerical experiment to look at this. So we put a dense enough suspension, right, in a drop, 2D drop, and we let this go. I'm coloring here with the black dot the direction of swimming for these particles, and the red ones are just to visualize certain individuals. And you'll see that organization starts at the boundary and it quickly organizes, right? So you'll see there swimming and you get this spiral vortex flow. And if I hadn't put the black dot to show you like the direction of swimming, you would just see that the ones on the sides are moving in one direction, right? The ones near the boundary, and the ones in the middle are moving backwards, right? But this is essentially a stable structure. It can organize left or right without any bias. And it essentially continues like that. And this is just like it's in the experiment, right? So you get this vortical motion that is stable. So what the simulations showed is that the swimmers are always pointing outwards, but the ones in the middle are moving backwards, right? And this was different from the initial interpretation, but this was showing that the fluid flow essentially is causing this double vortex motion. So, of course, we had to check with new experiments. So we got some mutant bacteria from Howard Berg's lab, Daniel Kearns, and they could color the cell membrane and the flagella with different essentially paints and visualize it at different times. So you could tell in relation to how the body and the flagella are positioned, in which direction the cell is moving, and also in which direction the cell is pointing. So the long story short is that the ones that are near the boundary are moving in the direction they're pointing, right? So but the ones in the bulk, they're moving backwards. So something is pushing them backwards, and since everything else has been eliminated, it has to be the fluid flow, even in this very, very dense case. So this is essentially proof by experiments that the simulations got this part correctly, right? So the fluid flow was crucial. If you do simulations, you can turn on and off various components to see what is causing what. So as I mentioned, if you have the elongated shape, right, like aspect ratio around 5, just like in the experiments for Bacillus subtilis, and the fluid flow, you get this boundary layer and double vortex motion. If you turn off the fluid flow, right, so you just have self-propelling ellipsoids in confinement, you will still get self-organization in most times, right? So all the particles are moving in one direction, but it's only in one direction. You don't get this boundary layer, right? All the reversing of the motion. And if you have instead spheres or disks, even with hydrodynamics, you don't get this self-organization, obviously because spheres have a hard time aligning. So you need both the ellipsoidal shape and the hydrodynamic interaction to get the motion that is seen in the experiments, right? So this is what the experiments and the simulations revealed. Now, when do you get this ordering? You get this ordering for a certain a range of drops. So if the drop is too large, the suspension will revert to this quasi-turbulent behavior. If the drop is too small, they don't have space essentially to move. So there is a range up to about 70 micron when you get to see this self-organization into a vortical motion, right? Just due to mechanics. So in the simulations as well, this comes out, right? This length scale. So if you confine the bacterial suspension under this length scale, the dense case, it will organize into this vortex. So what did we do next? Well, we confined the bacteria in a racetrack. So, and they just start to flow left or right without any bias. And for simulations, racetracks are also nice because locally a racetrack is just a periodic channel. So one can modify the method accordingly and see what happens. So what do we have here? We have a lot of these elongated swimmers in a channel, and you will notice that the ones at the boundary quickly organize and move at an angle, right? And they coordinate with the other layer at the other boundary, right? So they're moving at a non-trivial angle, right? Not zero, not low, something in between. And their flagella are pointed in the same direction as the other layer, right? And they essentially generate this fluid flow, push with their flagella fluid flow in the opposite direction. So the fluid flow that emerges is in the opposite direction that these two layers are moving. And it is this fluid flow that carries the bacteria in the middle. Okay? So the bacteria in the middle are being just washed back by this fluid flow. Okay? And if you turn off the fluid flow, you don't get this organization, right? You may get some local alignments due to shape, but no streaming, right? No streaming of bacteria. And of course, we used the experiments as well to check that is this correct? And indeed, they revealed that the bacteria at the sides, right near the boundaries, are moving in the direction they're pointing, but the ones in the middle are swimming against the flow. They're mostly just being carried back by this fluid flow. So the same story, right, emerged, that it is a cooperation of bacteria just due to mechanics, right? That the edge bacteria are generating fluid flow, which carries back their, which carries this, the ones in the middle, right? And what you see in the experiments visually is the ones in the middle that are being carried by this flow. And you see this organization for also a range of channel widths. So if the racetrack, the channel is very narrow, you will see this streaming flow, right? Kind of one peak plus a lag flow. And the bacteria in the edges have their flagella pointed in the middle, right? So they are kind of cooperating that way. And then as you increase the channel, you start to get a more irregular kind of peak, which breaks down into two or more peaks. And then at around 70 micron, this breaks down and you start to see vortices, right? And the edge bacteria also start to point out in different directions. So we observe this crossover from a laminar kind of active matter flow to turbulence, right? So if you confine this bacterial suspension under 70 micron, you most likely will see this streaming flow, right? And the 70 micron is the same one that we saw in the with a drop, right? So again, it seems that for this particular species, Bacillus subtilis, with a particular length, about 5-6 microns, this critical length scale emerges. And so if you confine the suspensions in channels or in drops with, under this length scale, you will get this organization. And this, I found it very peculiar that this is the same length scale of transient vortices in unconfined suspensions. Whether this carries to other species of bacteria, I don't know, but it would be nice to see. I argue with Wilson Poon a lot on this because he did some experiments. This was the group in Edinburgh. Alex is, I think, listening. So they confined bacteria in a spherical drop and tried to see if the drop will move. And they did not see this organization, right? So they did not see a vortex. And why was that? Well, that is because they used E. coli. And E. coli is a plumper bacteria, aspect ratio about 2, right? So it has a harder time aligning. And Hugo used Bacillus subtilis, right, in our experiments. So it seems that this shape is one aspect, right? The other one was that they used a spherical drop, right? And the sphere does not have an axis of symmetry, right? While a drum, our drops were drum shaped, they obviously have an axis of symmetry for things to organize against. So you see this by having the right, the aspect ratio matters, but also the confinement shape, right? Not just any spherical drop, it has to have some sort of axis of symmetry. And this method is very versatile, as I mentioned. One can do moving domains. So here we have a peristaltic pump. So the membrane, or essentially the pump boundary, has a preferred shape, sinusoidal shape. People use peristaltic pumps for various mixings of materials. So we put swimmers in this, right? And also a dye field, black and white. So if you have so-called movers or neutral swimmers that don't disturb the fluid flow, right? They're just self-propelling, so it's a bit unphysical. Then sure enough, they're swimming around, they self-organize, but you don't see the dye field getting mixed, right? Because there is nothing to break the up-down symmetry of the flow. However, if you have pushers like bacteria or pullers like the algae, the dye field gets mixed. And with pushers, it gets mixed pretty fast, right? You will see that the dye field, black and white, because the pushers will swim collectively and also mix the material. For pullers, there is also a little bit of mixing, but not as efficient as the pushers. The pullers are also dragging some fluid flow along, but nothing, again, as efficient. So one can think of using swimmer suspensions to enhance or hinder mixing or transport of various materials, right? So this was just a numerical experiment in that direction. Other things that we can add is, for example, various other fields. For example, we can add a chemical field. So each swimmer, like so chemotaxis, each swimmer generates a chemical that other swimmers are attracted to. Right? So chemotaxis is well known for bacteria and Spermatozoa. So if you just have neutral swimmers, so no fluid flow, they will just chase the gradients and essentially aggregate into these circular spots. And the circular spots are pretty fixed and stable. But as we've talked so far, is that if you have bacteria, you also have fluid flow. So what happens if you include the presence of fluid flows, right, for pushers? Again, you will start to see the seeding of these small spots, right? So to the eye, you see this aggregation, but it's no longer static spots, right? And they are not just circular. You have these moving droplets, and right, and they are very dynamic. So you get this dynamic aggregation, right? So if you include the chemical field and the fluid flows, you get a very different behavior. So essentially, this method can be used for a variety of things. We can include chemicals, we can include viscoelasticity, non-zero Reynolds number, and so there are pros and cons, as I mentioned, with this method, right? We can do a lot of shapes, we can couple the dynamics, we can do something other than Stokes flow. It can get computationally expensive, especially if we resolve the swimmer a lot more. We cannot resolve the fluid flow close to the body as well, but one can refine, right, using this kind of raspberry method. So it's pros and cons, right? So with that, started to experiment with other swimmer models as well. So one other model that people have known for a while is beads and springs. And you have two beads connected by springs. You prescribe the flagellum force in one of the beads, for example, for bacteria, and you get the bacterium, right? You do balance of forces and torques. And what I did is I added a counter rotation of the head and tail, because that's what bacteria do, right? So you have this torque, right? The torque dipole on top of the force dipole, right? And it's still a very simple model, two beads, right? So computationally, this is good if you want to look at collective motion, and you can vary the shape of the beads in case you want to do an asymmetrical swimmer to kind of mimic spermatozoa, and add more beads if needed. So does this matter, this torque dipole, right? So the fluid flow, if you look at the cross section along the swimmer, of course, it looks like this force dipole, fluid flow coming out in the middle, going out at the front and back. But if you take cuts along the head and tail, you will see that this rotation of the head and tail induces a lower order fluid flow. And you will ask, does this matter? It does if you look into confinement, because if you don't have this torque dipole, you can aim one of the swimmers at the wall, it will hit the wall and then swim straight. But if you add this torque dipole, the swimmer will hit the wall and then move in a circle around the wall. And this is what you see in experiments, right? Bacteria in a no-slip wall, they go in clockwise direction. At the no-stress interface, they move in the counterclockwise. Right? So this is a new model, and wanted to test, well, what's different with this model is the pair interactions, right? So far, we've been using the fact that two swimmers, right, two pushers, as I mentioned before, they come together, they collide and co-swim. But if you add this torque dipole, they don't co-swim and stay in a plane. They actually roll over one another and then continue to move out of plane. So the pair interaction, it's non-trivial. Right? It's not just an aligning interaction. Right, so most likely this is what happens in experiments, right? Bacteria, because they have this motion, you don't see aligning for a very long time. And also, if you have, right, not just side to side, but also head to head, the motion is no longer in plane. And this has implication, obviously, the pair interactions. But yet another model. So the pair interactions, you can get them to move out of plane or to roll over, right? The motion, that's the story is that the motion is no longer in plane. What else can we do? Well, we can add various obstacles. For example, you aim one of these swimmers to a solid sphere. Right? So if you don't have a torque dipole, the swimmer will hit the sphere, will slide alongside it for a little bit, and then will scatter away. But if you have a torque dipole, it will be diverted, right? In this case, to the right. So because of the rotation of the head, right? And if you have a bigger sphere, the swimmer that is just a force dipole will hit the sphere and swim alongside the equator. But the one with a torque dipole will span a smaller trajectory, circular trajectory, right? The other thing you will notice is that this is a large enough sphere and the swimmer is entrapped, right? So you can think about choosing, here's another length scale that comes. If you choose a large enough obstacles, the swimmers can get entrapped, right? So, and then one can modify this to have a swimmer inside a solid cage, right? So here, and again, the one with no torque dipole will swim alongside the equator, but the one with the torque dipole will span a smaller circle, right, inside. So why are we looking at this? Because we want to look at migration of bacteria through a porous material. And people have started, like the group of Sujit Datta at Princeton, has started to look at this, right? For example, gel beads and how bacteria move into them. And it's completely different from what people see that happens in unconfined spaces, right? Your typical run and tumble, it's essentially now different because you are in a porous material. So we want to essentially mimic this kind of environment, right? A connection of various obstacles or pores. Another one is you can modify this by modifying the bead side. You can look at kind of quasi-spermatozoa swimmers. One can even add the flagellum bead, right? A time-dependent oscillation. So what happens? You put one of these spermatozoa-like swimmers above a wall, it will do this circular motion. And then you can also add things like pillars, cylindrical pillars. And I know a lot of you are muted, but the question you should have is, oh wait, what about the method of images for cylinders? It turns out there isn't one for Stokes law, so we approximate. And the approximation can be pretty good. And considering that the method is very minimal, it does not seem that we are losing much, right? So here in this example, in the bottom, the swimmer hits the surface and then will swim alongside the cylindrical pillar, right, at the confluence of two surfaces, and then scatter away, kind of go on its way. So what happens if you have a very small pillar, right? So small diameter, the swimmer barely acknowledges it and kind of swims around. If the pillar is a little bit bigger, then the swimmer slides along this for a little bit, but then scatters away. Now, if the pillar is much larger, just as it happened with a solid obstacle, the swimmer gets entrapped and swims at the intersection of the cylinder and solid wall, right? So the swimmer is entrapped. And one needs to know about these length scales if you're designing structured environments to do various things, right? So if you are if you're building various environments to entrap or enhance swimming, right? These are important. For example, I'll mention this since we are here. There is this species of bacteria called Vitellovario, something with V. It actually hunts E. coli, and it knows that the chances are higher if you look at walls, and not just straight walls, right? Because then you have a 2D surfaces, specifically intersections of walls and obstacles. So its search space gets diminished from 3D to 1D. So it will just follow essentially the obstacles where they meet the wall, and it knows that the chances are higher there to meet E. coli. So anyway, length scales are important. So the last model I wanted to talk about biological swimmers is chlamydomonas, and it's been known for some time that the best way to describe this is by 3 Stokes sleds. Not 2, right? It's still a force dipole, but 3 Stokes, like 1 at the body and 1 each at the flagella with half the strength. So one can easily build a model that takes this into account. So 3 beads, not 1, 2, but 3. And remember, chlamydomonas is a puller. So the fluid flow comes in the back and front and comes out at the sides, right? In the time average. And one can add the flagellar bead, but to start with, we just do this just time independent, like constant flagellum propulsion. And again, one can add confinement, say a straight wall. You aim chlamydomonas at it, right? A swimmer like this, it will hit the wall. I'll play this movie again. And you will notice the flagellum touches the wall, and because there is spring forces connecting this, it squeezes, and then it will scatter away from the wall. So pullers scatter away from the walls. And you will notice that the outgoing angle is very different from the incoming angle, right? So it's not straightforward. This is what you see in experiments. So chlamydomonas scatters off a wall by using its flagella. So it kind of touches the wall and then scatters away in this manner. And one can check that one needs both the hydrodynamics and the triangular shape to get this correct behavior. And the idea is the outgoing angle is dependent on this triangular shape, right? Kind of the envelope of the body and the flagella. As the swimmer hits the wall and then turns there, this triangular shape determines the direction, the outgoing direction. And one interesting thing we saw is that depending on, for the model, depending on the incoming angle, you get different regimes, right? So if the angle is too steep, the swimmer will be stuck at the wall with the flagella at the wall. If the angle is too low, then it will barely acknowledge the wall, right? It will just take a small dip. We call this like the hydrodynamic escape regime. And then there is the region where we talked, right? The in-between region where it touches the wall and then it will scatter away. So if you measure the impact time or the time it spends at the wall, right? In the trapping regime, this is infinite. In between, it's a quasi-linear time because it takes time to turn. And if it's not touching the wall, right, the time is 0. And you can add noise, right? You can add Gaussian noise to the beads, and that will only move this asymptote, right, for the trapping time just a little bit further. But there is still an infinite impact time there. However, you look at the experiments, and this impact time is definitely finite, right? You get this quasi-linear behavior in between for the scattering regime, but then for high angles, it's definitely finite. So the swimmer is never stuck in experiments. Right? So what happens? Well, it turns out that chlamydomonas spins about its axis, right? So this spinning, is it important? Turns out it is. So if you have a swimmer that is going next to the wall and you turn on this spinning, it can turn into a more favorable position and then can scatter away, right? So you'll see in both of these, right? If you turn on the spinning, the swimmer will turn and escape confinement. And we checked this with experiment, right? So Matteo Contino and the group of Marco Polin did the experiments for this with a cylindrical pillar. So this is what you see. This is a cylindrical pillar from above, and you see chlamydomonas going near it, right? It's turning. And then you will notice after it spends some time around the pillar that it will scatter away. So this particular obstacle shape cylinder was chosen because it's easier to distinguish the various regimes. And indeed, these regimes came out, right? The trap and scatter by spinning, touch and scatter, and the hydrodynamic escapes. So we saw this in experiments. And indeed, just as before with the flat surface, with the cylindrical surface, the spinning of the algae is what enables it to escape entrapment. Right? So for the algae, the interaction with the solid wall, it's 3 distinct regimes that depend on the incoming angle, right? It's not a simple rule. And last, I wanted to talk to you about some more recent work on phoretic rods. So I mentioned that experimentalists now can put together this gold, platinum, or different metals, and if you put them in the right solution, like hydrogen peroxide, they will swim. So what we did differently is that we varied the ratio of gold and platinum to see if we get different dynamics. And that was the first thing. The other thing is doing a math model and simulation of this entire dynamic is actually very difficult because you have electrostatics, you have the chemical interaction, right, the ion exchange. So if you want to do a detailed work on this, it gets hard. So instead, we wanted to minimize this or to simplify this into a hydrodynamic model. So the idea is that where the junction of gold and platinum is, that's where you have the ion exchange, there will be a slip layer, right, on the surface of the rod. We don't know the size of this slip layer, right? So for our simulation purposes, we say, well, let's pick half, right? So, and we can model this as a conglomerate of these blobs for our numerical method, right? So that it resolves the closed fluid flows a bit better. right? So it's essentially we take the problem and turn it into just a hydrodynamics one, where you have this raspberry kind of rod, solid rod with a slip layer, right? That has the length of half the rod. So the typical Jano swimmer, half gold, half platinum, turns out to be a quadrupole, right? With a slip layer in the middle. If you get the long gold and short platinum, the slip layer will be in the front. And what has the propulsion in the front? Poolers. And indeed, this has the pooler fluid flow, right? The fluid flow comes in the front and back and comes out at the side, right? So long gold is a pooler. And short gold, right? The slip layer will be in the back, right? The propulsion. And that is a pusher, right? The propulsion layer is in the back, that would be a pusher. And indeed, the fluid flows that you get are that fluid flow coming in the middle and going out at the back. And we wanted, right, the numerical method. We have to maintain the rigidity of this. It's a bit more complicated. There is noise prescribing this activity, right, the slip layer. And we looked at rheotaxis. So what is rheotaxis? Biological swimmers do it, bacteria, Spermatozoa. It's essentially swimming upstream along a wall, right? So you have confinement, a wall, and swimmers and fluid flow, some shear flow, and the swimmers swim against this flow. So if you just have no flow, you can have swimmers of equal probability, right, front and back. If the swimmers are immotile, they will just be pushed back by this flow. And like you can see this figure here, right? They're pushed back by the flow. And if you have, motile swimmers and flow, they will swim against the flow. So that's rheotaxis, right? And so these artificial swimmers also do rheotaxis, and this has been known, right? But which ones are most efficient? If you need these swimmers to do particular work, which ones will move faster upstream? And if this is not intuitive, turns out the poolers are most efficient. So if you are designing swimmers that you want to get upstream faster, you have to pick poolers, right? That would be long gold. Why so, right? So our hydrodynamic model shows that poolers are most efficient because they move at a higher tilt. And because they have a higher tilt, they are more responsive to flow gradients, right? So, and pushers are actually the least effective. So, and this is just for rods, but one can use this method to look at various other shapes. And the other thing that we're just submitting this now, it's gravitaxis. So what is gravitaxis? It's moving against the gravity. So you have a tilted table and these swimmers can move against gravity, right? They will move up. We have to choose, however, rhodium instead of platinum because there is a density mismatch and that's what will tilt the swimmers, right? There is no imposed background flow, right? There is just the tilt of the surface. And indeed this happens, right? Because there is a mismatch between the center of mass and the center of hydrodynamics, right? Which will give it the torque and enable it to move upstream. So what is the ultimate goal, right? Why did I tell you about all of this? I'm extending all these existing models of bacteria, microalgae, spermatozoa, and looking at them in various confinements and geometries because I want to approximate their motion in natural habitats. And the objective is to include the correct physics. And then one can put this in the computational tool of choice, whether that is immersed boundary method or, as I'll show later, some other ones. And we want to include enough correct physics and then develop the tools that can handle the dynamics, the coupled dynamics of thousands or even billions of this. Of course, there is a lot of technological applications, right, other than the lab. For bacteria, you can design various surfaces that are antimicrobial, you can utilize them for work. So microalgae, I mentioned before, one needs to understand their motion and confinement to engineer better photobioreactors. As spermatozoa, there is lots of technological applications for them, and active colloids, people are very excited about this. They can be made to do work. So it's still, they hold a lot of promise, but I'm not sure about what. So what do I want you to remember from this talk is that the interaction with the wall are a complex interplay of the direct contact, which depends on collisions, which depend on the shape of the swimmers. You have hydrodynamic interactions, and then you have to take into account swimmer particulars, for example, spinning of the head and flagella or spinning of the whole swimmer. And interactions with obstacles or confinements sometimes reveal length scale, right? If you want to confine bacteria or spermatozoa. And the models in the simulation specifically are tailored to the swimmers. They're minimal, but as you saw, for bacteria, you need the elongated shape and hydrodynamics. For the algae, you need the 3 beads. For spermatozoa, you have to take into account the conical kind of envelope. And this will hopefully help us to understand better the swimmer interactions with confinement and how to control collective motion or individual motion. And we're currently scaling this up, right? So wall interactions cannot be described by a simple rule, whatever that may be. And pair interactions are also not simple, right? And this has implications for coarse-grained theories. So if you're building continuum theories, it won't be as straightforward. So I mentioned that current work, we're scaling this up to compute hundreds of thousands of these swimmers. So this simulation here is bead-and-spring swimmers, bacteria. This aspect ratio is 2, so it's pretty low. But we have full collisions and hydrodynamics in a periodic box. So it's 50,000 of this. Just showing this as an example. Of course, it's computationally heavy. It has to run on cluster. And the method works, so we can extend this to various types of swimmers like chlamydomonas and so on, and include particular. And the other challenge was doing, as I mentioned, confinement, so that it becomes a little bit more. The video for that is very large. I hope it doesn't get stuck. So here we have 100,000 dipole swimmers above a wall. It's doubly periodic on the sides, and there is a membrane on the top so they don't escape. And for the interactions, we use the kernel-independent fast multipole. The video is very big, so I'm not sure how much it's transmitting. But you will notice this large-scale collective motion and plumes of swimmers. So there is a lot of aggregation near the solid wall, and then there is swimmers moving collectively, locally aligning and generating fluid flows on large scales. We are refining these models to look at simulations of swimmers, hundreds of thousands of this, right? So I think to date, this is one of the largest scale ones, right? So 100,000 with confinement. And with this, I will stop. So thank you for listening, and please, if you have any questions, let me know.